So remember, we have basically Big 5 in the introductory statistics course. Difference, or single proportion, difference of proportions, single mean, one sample mean, two sample means, whether it's paired data or two independent sample data. The general format that we have for these did not get in there. My computer crashed and did not. Did not get in there. So let's go ahead and write it out on the board or on here. So remember that there are two parts. One is for confidence intervals. Basically, we have our estimate plus or minus our multiplier times our standard error. And this, in general, is the idea that we have for any confidence interval. Some of it might be just plus, some of it might be minus, depending on whether you're going for a one-sided or two-sided. The other possibility would be a statistic is equal to our estimate minus our null value divided by the standard error. In some sense, the estimate minus the null tells us how far we are away from our expected value, and then we divide by our standard error to measure each step. So usually it would be a Z or T distribution for this one. Your multiplier would be a Z multiplier or T multiplier, depending on the situation. So part of your ideal goes back to what we did the first week. Are we talking about categorical data and we're trying to find out a proportion, or are we talking about quantitative data and we're trying to estimate a mean? Because both of those are the center. So we're just going back to August, trying to determine where we are, and then are we doing a confidence interval, in which case we're estimating the parameter, or are we making some test about it, or trying to determine whether some claim about the center or whatever is appropriate in our situation. So let's pick it up and talk about some other ideas. So first of all, we want to try to use comparison to identify causality. We're often interested in comparing two treatments. For example, gosh, I can't remember its name. What was the one back that was said it might be a good repetitive measure for the virus, but then they took it off because there's a lot of variation.
Chloroquine?
Whatever that is, yes. So the question is, does that work or does it not work? And so we want to make two tests to determine whether or not we have a response. And so the first one you need to know, first kind of idea you need to have is the treatment versus the control group. Treatment group gets the treatment. The control group does not get the treatment, and so you're looking at figuring that out. If, on the other hand, the objects are used for comparison and are not assigned to investigators, then we're said to be observational. Again, this goes back to our open intro reading that we've had before. Just kind of a reminder, we have an observational study or we have an experiment. Let's talk about why an observational study may not be so good as far as making conclusions. The reason is, with an observational study, even though it may indicate a statistical significance between the two groups, there may be some other underlying factor, some lurking variable, some other causing it, some sort of variable that might be the reason for the part. So we have to be aware of this type of thing, because you may look at it and say, hey, we looked at people who drank coffee, they had a lower suicide rate than those who didn't drink coffee. What might be a reason why people who drink coffee have a lower suicide rate than those who do not drink coffee? Yeah?
They would have a probably higher serotonin response.
Higher what?
Serotonin response.
Higher serotonin response. Okay, you have to explain that for me.
The more the serotonin is in your body, the more depressed you get. But if you have an increase in serotonin, it's less likely you feel depressed.
Okay, so it could be due to the coffee that they have a lower suicide rate. What are some possible explanations? Yeah, Calvin?
A lifestyle. So like if someone starts every morning and just kind of relaxes and has a cup of coffee before they start their day, it can be a better start to the day, which overall can be a better
Possibility? Okay, so a relaxed heart, but so that might be a lurking variable that it's not so much the coffee, it's starting off a relaxed day. What's possible another explanation? Well, there are a multitude of possibilities. It may not be due to the coffee if you look at it backwards. It may be that those people who drink coffee go out to coffee shops more back in the day and have conversations. So it might be the human interaction that might be the reason rather than the coffee itself. Now, if you look back, you may not get, or an observational study, you may not get a cause-life example. It might be causation. Just because you have correlation does not mean you have causation. So in 1978, they looked at male physicians who graduated from Harvard and looked at who died between 1974 and 1977. And in this example, there were 125 who went into practice. 125 of them lived to an average age of 48.9 years beyond graduation. So I don't know, 78.9 or something. And those people who went into academia averaged 43.2 years after graduation. Okay? So it appears that who lives longer? Those who went to practice. And maybe they saw patients, had a better life, they got more relaxed at conditions, they're in their ivory tower, thinking up ways to make life difficult for students, all those kind of things. So does the data suggest that the mean lifetime after graduation for doctors in full-time practice exceeds the mean lifetime for those who have an academic affiliation? All right, so this would be a difference of two means. So that would be our test, and we would do a t-test. Of course, this is so large enough you could use a z-statistic if you'd like to. So our null hypothesis that we might set up here is that you had two choices. One is our null hypothesis. You might say, well, the difference is 0, or probably the way I would like to say it is that you live longer. Your average life expectancy exceeds the mean lifetimes for those who have academia. So I would write this out in symbols, and I'd also write in words, where mu1 is the mean lifetime beyond graduation in full-time practice. U2 would be the mean for academia. And so our alternative hypothesis would be that the difference is positive, or in other words, mu1 is bigger than mu2. Yes!
Did you mean to write mu1 equals mu2 on the...
I did. Thank you. I was already cooking the books, so to speak. Okay, so this is a 2-sample t-test for means. We've set up our null hypothesis. Now let's see what kind of assumptions we need to check. Random sample? What do you think?
We have a large, we can assume, even though it's not explicitly stated.
It's kind of questionable in my mind because all he did was just look at the obituaries. But we'll say it's okay somewhat. And then what about normality? Do we need to check the normality plot for this situation and see if it's normal? How come? Yeah, so both are greater than 30, so we're okay.
Wait, why is the random sample in question?
We only took a sample over years and didn't take a random sample over ballparks. So it's okay. It's just not sampling for an entire population. Yes.
So if they're using data from the whole population, like the Harvard graduates who died within those years, isn't that more like a census?
It is more like a census, and so we still could have some sense we're looking at all possible Harvard PhDs through this. So I guess it is a sample. It's just a little bit okay, a little questionable, but we could say it's okay. We can still make conclusions upon it, even if we're a little skeptical about it. So there we let U1 be the average lifetime, years beyond graduation's full time, and assumed to be 125 is in one and 90 in the other. And it doesn't take any information about the variance, so let's go ahead and just assign S1 to 14.6 and S2 to be 14.4.
How did you find those values?
We just made them up.
Gotcha.
No, we didn't make it up. It's just sort of looking at previous examples. We were just estimating what that would be. So in some sense, I guess we made it up, but I guess estimating sounds a little better than making them up. Okay, so what level should we test this at? Alpha to what? 0.05. All right, well, let's go with the standard. Hopefully we're not p-hacking too much. Will be the p equals 0.5. So you get out your calculator if you'd like. And let's take a look at the averages that we got. So you can go to statistics, or to stat. And then on to tests. And we'll do a 2-sample t-test, which is number 4.
When would you use a 2-sample t-test?
If we actually knew the standard deviation, but if we knew the standard deviation, then maybe why would we not know the mean? In some sense, if you have a large enough sample, we don't have to really worry about the degrees of freedom. In this case, with 100 and 190 divided by 89 divided by 90 is not going to make that much difference between the standard deviation. I just think in practice you should just use the t-test because the t-test becomes almost normal once it gets above 40 or so. So go ahead and enter in this data. The average was 48.9 with a standard deviation of 14.6. There are 125 in the sample. The average age behind graduation was 43.2. In the second one, its standard deviation was 14.4. And we have a 90 in the sample size for that one. And we want our alternative hypothesis to be that mu1 is greater than mu2. Again, I'm not a big fan of pooled data, although you could. In this case, I don't think we would pool the data because it's probably different enough to say that they're not the same. So I will hit no. Magenta is a nice color. And then I could go ahead and calculate this. And it gives me my t-statistic of 2.85 and my p-value of 0.0024. So in my results section, I'd have t equals 2.85 and a p-value of 0.0244. Let's kind of see how we would get that, just so that we know. Oh, just 1 0 or 2 zeros? Well, first of all, let's kind of figure out what our standard error is. If you go in the back of your book to the the B side of the forest green, section, you can see that we would take our differences within our sample and then whatever our differences that we're claiming. You know, if this were 3, we'd put 3 in for 0. Here we're saying there is no difference, so we could put 0. And so here you can see your standard error as S1 squared divided by N1, S2 squared over N2. You did enough on your homework this week that you're turning today and which you turned it on Thursday to show that the variance of X bar minus Y bar is S1 squared over N1 plus S2 squared over N2. So you've done that already, and then you can calculate the p-value as far as this one. So in this case, since we want mu1 bigger than 2, our p-value would be over here, so we'd have a right-tailed test. The question is about the degrees of freedom. You could take the minimum, or there's this formula called Welch's formula that's a little bit longer. This is a weighted average of the two standard deviations. And the nice thing about your calculator is that it already calculates it for you. What is the degrees of freedom according to your calculator? 193.4? Sure. So it becomes more Z-like. As a matter of fact, let's go ahead and even we can either draw the what it looks like, and here's my normal distribution coming up someday, hopefully. Come on, there we go. And it'll fill in what my p-value will look like. Anyway, it's very small. It filled it in. Just not very much. It gave me my p-value of 0.0024. All right, would we reject the null hypothesis in this case? Yes. And so the alternative, and say there's strong evidence actually that those who went into private practice live longer than those who went into academia. Tegan.
Can you go back over what the t-value really means?
Sure. If we take a look at the t-distribution, we're wondering where on this happens. This is the center, and so we're going to count how many steps out we want to go from the center. So the numerator tells us how far we are from the center, but we need to divide by the standard error, so we've got units away. So our test statistic here is 2.85. And so that tells us that we're 2.85 standard errors from the center.
What is 2.85? Like, what is that mark? balance from?
So you take your difference between the ages, which was 5.7.
So it's saying that difference of ages is way out here.
Yeah.
Which isn't likely.
But you got to standardize it. So you take 5.7 divided by 5.7 is the actual difference in age, but then we have to divide it by the standard error so that we get the same, standard errors away from the mean. And so it tells me I'm 2.85 standard errors away from the mean. And then from that I can find my p-value. What's the probability? I'm presuming the null hypothesis is true of obtaining a result as favorable or more favorable to the alternative hypothesis based on our test sample data. So you could put this into your calculator. I put a very small number to 2.85. Actually, I probably should have put 2.85 to a very, very large number. And I got 0.0024. And if it was so large enough, you could actually use the z-test and gotten 0.0022. In either case, your p-value is less than or 0.05 in favor of the alternatives, and that's consistent with the report in the letter. Can we then conclude that going to academia is not as likely for Harvard physicians to live as those who went into private practice? And here's where the issue comes into effect. Our data suggests that, but that doesn't mean that that's going to give us a good reason going forward. And here's the reason why. What we did was we looked at a retrospective study. And that's a good word to have, so write down retrospective somewhere in your part. Retrospective studies is not as possible, do not tell us as much information as a true experiment. We did not set out and take a sample doctors that were going to go into academia, randomly assign others to go into practice, and then compare. So this retrospective study does not establish that going into practice will have you live longer. The same thing happened when they started comparing conductors. These conductors, orchestra conductors living in 90, 93, 94, they said, hey, look, if you go to become an orchestra conductor, you will live longer than the average person. The problem was, how do we know that there weren't people at age 22 and 23 that wanted to be a conductor, but then had died for some reasons from being a conductor? The tuba fell on them or the heart fell on them and they died musically, but still rather tragically. And so looking back does not give you an explanation, and that's kind of where our struggle is in a lot of situations. We're looking back. That gives us evidence, but doesn't establish causality. Evidence versus causality.
So in that case, are we assuming that there's some underlying factor?
There could be some lurking variable that we didn't take into account for. It could have been that during a particular period it was a very stressful time in academia and something happened that was in addition to that. So it wasn't necessarily that that was a plausible explanation. Maybe those who were in academia were more likely to go to war and work on something and be around Agent Orange or something, which would still be that case maybe at that time, but going forward, that does not establish it for the future. There may be some other variable that goes into play. One of the most controversial, one of the most controversial studies was where they separated twins at birth. They were identical twins, and they lived with one family and they lived with another family. And so there was a situation was you would see equally likely, if their homosexuality was the environmental influence or not, then they would be at the same rate, but even if you lived at the same time, maybe you saw the same video. I mean, there's all sorts of things that just didn't. It was attempted to be a double-blind experience, but there were a lot of ethical issues behind it. There is that story. Did we talk about this story in this class, or was it another class? We talked about this person went to school and there was someone that looked exactly like them. They found out that they were brothers, and then they found out they were triplets, and that they were separated at birth in a variety of different ways. So I mean, it was just, and then lots of counseling. So it was just horrible. I mean, I could see it in science, but it was not good personality-wise. So observational study has been used a lot to find causality between those things. You really have to take into account some other things. So the best way, at least in the statistical way, to determine causality is a randomized controlled experiment. And if you take a look at page 85 in your course pack, it talks a little bit about random and double-blind experiments. The other possible place you could look at is in the Open Intro book that we've referred to quite a bit. So what you do with it, just again kind of reviewing what we had with the randomized control group, what you do is you randomly select assignments. Yes?
So what do you do in situations where you want to establish causality but there are ethical concerns?
Yes, those are quite challenging things. You have to go in indirect ways so you don't get as much things. So, for example, right now, should we inject people with the virus and see if they live or die? It's not very ethical at this point in time. So that's why we use mice and other things for that. But it is an issue. I mean, the horrible things that were done during World War II. You know, they took breaks on one leg to see if they could heal or not between the twins and stuff. That you just can't do that. I don't think. So that's always trying to find a different ways for that. And we'll talk about that shortly. So randomly assign two people and you compare and you try to make them as similar as possible. The idea then with that is if there is some sort of lurking variable, it will affect both sides equally likely. That's the theory behind this. Randomly assigning them to two different groups. If there's a lurking variable that affects one, it will affect the other, and you'll get a pretty good comparison between the two. That's one that students, many people will say, well, no, because you randomly assign them to two things, but maybe this group had more smokers in it than this other group. You can do some sensitivity analysis as well, but the idea, though, is that there's a lurking variable that's equally likely to be on both sides. And then you compare. We talked about this before, double blind, that neither the researcher and nor the subject knows what's going on. Because if I get a treatment, maybe I'm going to try to run a little faster and do more exercise, help out the researcher. Or maybe if I think it's working, I'm going to go out, storm the field after a big win, go to bars. I guess we're still in the political season, so I can't. Okay, so we can, and then maybe you can increase the sample size to also increase your probability, because remember your standard error will go down in that sense. Another way you can do it is blocking. What you do is you divide people into different subgroups, like men and women, and then you randomly assign each one of those groups into a treatment group and control group. So that's another way of doing it in terms of blocking. So the variability is less within each block, and maybe produces a better effect as far as how well the treatment may work. So here's a traditional example of a block design. You have males and females. You randomly assign some to get the placebo, randomly assign the others to get the vaccine. What is the placebo?
Just like a sugar pill.
Either a pill or a sugar pill or maybe some other treatment that may or may not work. There have been lots of tests that shows that the placebos will cure a headache more than aspirin, just because of the psychological part of getting some pill from this. And matter of fact, my niece's son, when he's sick, he goes, "Mommy, I want a placebo." So they go and mix sugar and water together and give him the placebo. And I try to do the same thing as a parent. Try to say, hey, this will work even though it has no medicinal value whatsoever, because I don't want to have the other side effects with it. Lauren?
For this case, when I have like 4 different statistics, what test do you use?
Well, you would compare the t-test between the placebo and the vaccine, and then the t-test for comparison between the females. And
So
within the
you
place.
wouldn't be comparing male and female?
I don't think so. For a hypothetical medical statement. I mean, if you did, you wouldn't have the placebo and vaccine. You could, although you can, there may be some situations where it could be that it may, these should be equal.
Like you want to say a vaccine helps females versus male, I don't know.
Yeah. In some sense, you can compare the rate here of different proportions of health versus this proportion. Now here's some ethical concerns. In any experiment, there must be sufficient doubt and sufficient belief when you run an experiment. You need to have sufficient doubt and sufficient belief. What do we mean by sufficient doubt? A little bit broader than that. Go a bit bigger before why we will run an experiment. We have to kind of believe that it may not work. Otherwise, give it to everybody, right? If we have a treatment for the virus and we have no doubt that it doesn't work, why not just give it to everybody? What about sufficient belief? In what? We have to believe that it might work. Otherwise, why are you spending all this money and exposing these people to harmful side effects to try to do an experiment? You should be able to experiment what a double-blind experiment is, and randomization does for experiment. It allows to minimize or control, we would say, the lurking variables. If something happens to one group, it's equally likely to happen to another group if there was a multiple one. And we talked about the placebo effect. So we can't just give you a treatment and observe, because there might be something else that happens. There's been plenty of studies that if you tell like graduate students that this mouse is going to be faster, all their data will show that the mouse is faster, even though there's no difference whatsoever between the mice. I know none of you have ever done this in your chemistry or physics experiments, right? That this is the data you're supposed to get, and somehow your data doesn't work out. So you kind of like, well, let's round off here and add a little bit here and have it works out. I know none of you have done that, but yeah, still the same idea is that you have to compare with the two. All right, let's go now to the mean of paired differences. This is like section 9.3. And we talked about this case with the blood pressure. We measured their blood pressure before they went to the dentist and then when they got to the dentist or after the dentist. Now, can we say those two things are independent? No, because we're looking at the same person. We want to see what happens with the drop. So Here's the average increase of your blood pressure going up 5.7 points with these 10 people with a standard deviation of 6.02. And we want to use alpha is equal to 0.01 as our as our level of significance. So we do have to check conditions here. And this is where we do the normal probability plot. Does it appear that it comes from approximately a normal distribution? Yes, so we're okay because we don't have enough. We don't have 30 or anything for central limit theorem says we have to come into there. So even though we don't have bigger than or equal to 30, we go to the normal probability plot, and it does appear that it comes from approximately a normal distribution. So here we're going to use the confidence interval for mean pairs. Let's kind of go back to our data here, and let's maybe enter it into our calculator just to kind of see what we might get. 10, 5.7, and 6.02, right? 10, 5.7, 6.02.
What kind of test is this?
This will be a one-sample t-test now, because we're just looking at the differences and the averages. So I'm going to go to a test, one-sample t-test, or just a t-test, number 2. I'm going to input the stats. My mu naught is 0. My x bar is 5.7 as the difference. Yeah. My standard deviation is 6.02, and I have 10 data points. And I want to know if it increases blood pressure. So mu naught will be bigger than 0. I got to be on the right. Like that. Am I okay there?
Where do you get the mu equals 0?
Because that's my null hypothesis. I'm saying that there is no difference in the blood pressures. Okay? We could change that to say I'm claiming that it's going to increase my blood pressure by 2 beats. And we'll do that shortly.
So the only difference between this and the difference of means is that now you're averaging the actual difference?
The difference is I have before and after. Each observation is closely tied to before and after. With the difference of means, I have 2 independent samples. I didn't have one person die I didn't pair up the person dying who is an academia with the person who died with this. So they're not independent, they're dependent. It's before and after, husband and wife, freshman versus you as a freshman versus you as a senior kind of deal. And so then you could calculate this with their various values. So kind of compare if this is what you get. I should probably figure out the confidence interval here shortly too, huh? So if we go back to stat and actually, can you do a confidence interval?
7 and 8 up there.
7 and 8. Oh, t-interval. Thank you. So we've got the data in there already, and we changed our confidence level to 0.99. And we can calculate it, and I got it. Oh, because I had a 2-sided instead of a 1-sided. So it'll always give me a 2-sided?
Yeah, so then you have to make it like 99.5.
0.5.
Yeah, why is it so different?
What did I mess up on?
Are you sure? Are you comparing it to your 0.33 from the slide?
Yeah.
Are you sure that's right?
I'm not sure that the 0.33 is right. It may have been an inserted slide from another part.
Well,
So that would be at most 99.3. So I must have made a calculations. So there's something I'm missing here that I did not put in. Let's do it by hand. Well, what p-value did we get?
oh, I know what it's because it's two-sided, we need to make it 0.98 so that there's 1% on both sides instead of 0.995.
Oh, okay.
And when we do that, we get 0.33 as our lower bound.
Okay. So change this to 0.998.
Just 0.98, right? Because that way we have 1% on either side.
Oh, okay.
Then we have a 99%.
You're right. Okay, so the confidence level is 0.98. Right, so if we want a 0.1, I don't divide by 2, I need to do both. That's why it's always good to draw the picture.
Right.
So yeah, you get to 0.98. And so when we do that, because we have to try to trick the calculator, that way we get the 0.33. Is 0 within my interval? No. So I would reject the null hypothesis. So there are 3 ways that you can reject the null hypothesis. One is by the p-value. One is comparing it to the critical value. And one is comparing it with whether your estimated value is within your confidence interval. Yes?
Can you explain why we did 0.98 again?
We needed to do a one-sided 99% confidence interval, but your calculator only does two-sided. So that means we have to add another percent over on the lower ends. We do a 98% confidence interval and take the lower bound.
Why did we add 1%?
Well, because, again, the calculator can only do a two-sided. So if there's 1% on this end, I'm going to have to do another 1% on this end. And so I've got 2% total on the ends and 98% in the middle.
Okay. Oh, yeah.
Alex?
The comparison to the critical value to reject the null hypothesis, can you remind me of that one?
Yeah, so
Is that
if we wanted, what we'd have to do is we would draw our t distribution and we would have 0.01 at this end.
Right.
So we would do inverse t of 0.99, 9 degrees of freedom. And the test statistic there becomes what, 2.63 or something?
Okay, yeah.
What is it? .82. And so what we're saying is, here I stand, I can do no other. Anything test statistic is bigger than 2.82, I'll reject. Anything less than 2.82, I fail to reject.
Yeah, so it's the same. It's just like one step prior to
Yeah.
the p-value.
But I like the p-value because that allows the person to judge for themselves whether or not to reject or not. Because if it's like just barely over, you're still rejecting if it was like 0.000003.
So because the calculator only does a two-sided, that's why we have to have the percent.
Yeah.
So by doing that, that gives us the 99% confidence interval.
If by just taking the one bound, just taking one endpoint, that'll give us the 99%.
Right, but because in our calculator we have to add,
Because we can only do two-sided.
so that gives us a 98% confidence.
Yeah.
So then,
Taking one side will get a 99% confidence interval.
right,
It's
but
at
how do we
least.
go from our calculator to what we want? Our
Right,
calculator
you trick it, if you want a 99%, ask for a 98%. If you wanted one sided 95% confidence interval, ask for a 90% confidence interval. And then take the left bound or lower bound.
It gives you a 98% confidence interval. We're not getting what we're asking.
Is what?
If we're putting in our calculator a 98% confidence interval, we're not getting the 99%.
You'd be getting a two-sided 98% confidence interval, a one-sided 99% confidence interval.
Oh, so two said 98 is the same thing as one said.
You got it. So here's another example where if you're looking for clean drinking water, like when we had our boil water last time, for zinc, if you just looked at this, it doesn't really seem to be there a difference between the two. But if you think about the measurements for the upper level and the lower level, then you could kind of see that, okay, maybe there is a difference between the testing water. And so in that case, you would still do a paired t-test between the two. Okay, if you sign do I have to sign the sheet for the test? Have a good Monday.
I'm going to I saw on my website on Thursday too. Is that what time works for you on Thursday?
9:30.
In the morning? I have a placement for education that morning. Can you do anything? Afternoon?
I'm doing good. How about you?
It ends at 11, but then I have a doctor's appointment at 3.
Okay. You don't want to try to sneak it in before your doctor's appointment?
I can do that. Would you like 1 to 3 work?
Sure.
Okay.
11 to 1 or
Okay. Thank you.
Thank you.
Oh my gosh.
So the fun, will they take on Monday, like when we're already home?
Yeah.